No, we often talk about, I try to frame it in that way. It's a telescope pointed inside the Earth instead of looking outwards towards space. Right?
Yeah.
It's comparable in kind of scale of the projects, and what you're trying to do is an inward pointing telescope.
Hi, and welcome to Wonder, the Planet Earth podcast for curious people. I'm Holly Cook, joined as always by fellow Earth scientist Dr Anthony Reid, and we're joined in studio today by a marvellous Dr Caroline Eakin, all the way over here in the Pod Booth studio from Australian National University. Now, Caroline, it's a pleasure to have you here because Anthony and I have been spending a lot of time thinking about the Australian continent. And what we've realised is that there's actually so many different ways that as a scientist you can think about the Australian continent. There's so many ways you can imagine what this continent is. So my first burning question to you is, what do you even perceive to be, in your scientific craft, what do you perceive to be the Australian continent?
So I think my view of the Australian continent is going to be a lot deeper than the average person's view of the Australian continent. So we live at the surface of the Earth. We live on the layer that we call the crust. On continents, that's on average 30 to 40 kilometres thick. But in my view of the continent, I also consider the layer below that a layer that we call the lithosphere. And this is a strong, rigid outer layer of the Earth. And that extends down several hundred kilometres. So to me, the Australian continent is up to, say, 300 kilometres thick.
Oh my God.
In my view.
Mm-hmm.
And it's not just the rocks that we see at the surface, it's also the physical properties. So the strength of the continent, this kind of rigid or strong block that floats at the surface of the Earth, and how that moves with the tectonic plate.
That is really wild. So rather than zooming out to observe the Earth from space, which is sometimes what we do, what we've actually done is gone like 300 kilometres below the surface of the Australian continent.
Yes.
Fantastic.
Yeah.
Okay, so if we follow that thread, if we, in a magical universe, if we were able to transport ourselves down hundreds of kilometres and, I don't know, separate ourselves out from the rock around us and actually just look at it from a third person perspective, is it all the same? Is it like flat? Because Australia is so flat, right? And so is the bottom of the continent as flat as the top of it is?
No, absolutely not. There's a much bigger variation at the bottom. If you think of topography, the topography at the bottom of the continent is huge. So essentially the centre and western part of Australia, the oldest parts of Australia, are where you have this deepest part of the continent down to 300 kilometres. But when you look along the east coast, the sort of eastern third of Australia, there the continent, in my view, is only, say, 70 kilometres thick. So that's a difference of, I say, 230 kilometres, right? Versus if we think of topography, correct me if I'm wrong here, Mount Kosciuszko, that's what, 2,000 metres or something on the order of magnitude?
2,300,
Yeah, metres. So that, we're an order of magnitude, many orders of magnitude, much larger variations in the base of the continent than there is at the surface. Yes. Yeah.
That is just really, sorry, it's just so bizarre to think about. I'd been thinking about what I wanted to talk to you about, and that thought just popped into my head. Was like, so the bottom of the continent is actually ridiculously curvy. Yes. It's variable. Yes. It has curves, it has edges.
Yes.
Why?
Correct.
Why is that?
Why is that? A good question.
It feels like a big question.
Yeah, so it's because of the different ages of the continent. So this western 2/3 of Australia is the oldest part. So, 1 billion plus, we're talking billions of years old. And essentially that has been sitting at the Earth's surface for the longest amount of time. And if you think of the whole Earth, it's coldest at the top and hottest at the centre. So the part that's sitting near the coldest part, it's a thermal, so it's just sitting there getting colder and colder and colder and colder. And as it's getting colder, then it's getting stronger and forming this strong, rigid layer at the top. So that propagates down, creates this really thick lithosphere, versus the eastern part is much younger. So it hasn't been sitting at the Earth's surface for as long. It's only, in geological, it's only hundreds of millions of years old instead of billions of years old. And it's been accreted or kind of pasted onto the side of the continent. So it's been moved about, it's been reworked. So the lithosphere of the continent there is much thinner.
Gosh, that's a big difference, isn't there?
It's almost like tree roots. It's like roots. It's sort of the eastern side of Australia has just been pasted on, but the western part of the country has been sitting there growing roots in a sense.
Yes. Anyway, it just continues to grow and grow. Yeah.
Oh,
the simplest.
Weird. Okay, so if it's flat at the surface and it's so curvy and so topsy-turvy actually beneath the surface of the continent down into the lithosphere, how can you tell that? Because the sort of inside joke of geology is Australia doesn't have much outcrop. It's just flat dust, and we struggle around to find rocks. And when you find the 1 pixel on Google Earth that is an outcrop, it's a hurrah. So what? Is there any kind of expression of how wonderful and variable it is under there? Is there any expression of that at the flat surface of the country?
Yes, so this is a great question. This is one of the actual known sort of problems in Australia. This is called a concept of uncover. So up to 80% of Australia, as you're saying, is covered by a thin veil of sediment or a sedimentary cover.
And some would love that, but that's
which obscures the rocks, the continental rocks that make up the continent below. So that limits our geological information. But there are places where there is outcrop, where we know that in Western Australia and South Australia and Northern Australia that there's these really old rocks. So we can infer where they've different old building blocks of the continent have come together at these different ages. But how we know about the lithosphere and how we know beneath that, so that's a problem that obscures so much of Australia. So that's one of the reasons why we need seismology. So to be able to see underneath that, we need some way to sense into a solid body.
Yeah.
So a bit like getting a X-ray or a CAT scan of the body. We can use seismic waves that travel through the earth, see how fast or slow they travel, and then image these different layers, image the deeper parts of the continent. And we can use that to then map out where the bottom of the lithosphere, where the bottom of the continent is.
Do the seismic events that you are using to map out the deep continent, are they happening in Australia, or are they happening outside of Australia, or both? Where do you get this information from?
A bit of both. Mostly at the scale of the continent, we're using earthquakes globally, so earthquakes that happen anywhere in the world. So basically, any earthquake that's above, say, a magnitude 5 or above can be recorded anywhere in the world. Let's say, so we could pick it up.
Your machines are sitting out in the bush somewhere, listening. Yeah. Right? They're just waiting for the sounds to happen, and they sense subtle vibrations. Yeah. And you're saying that vibration can come from an earthquake that's happening in Peru or
wow.
Or Tibet or amazing, isn't it?
Yeah, it is, yeah. So it will depend slightly on the location and what part of the earth it's traveled through, but anything magnitude 5 and above would be able to be detected by seismometers.
It's almost like a whale, the sound of whales. Just the earth sort of talking to itself across vast distances.
I love that. That's so elegant because I'm glad you made it elegant, and I'll tell you something that's not so elegant. I'm glad you clarified what are the seismic events, like what generates the seismic waves that you then use to interpret the lithosphere. I sort of imagined, I went camping over the weekend and it was dark skies and I saw so many satellites. It freaked me out. And so my head went, is someone just pointing giant lasers from satellites at the earth and like Elon Musk channeling seismic events? So no, it's much more beautiful. You actually you're right, it's a natural thing. It's the earth creating and listening to itself, these seismic events, these earthquakes.
Yeah, they're happening all the time, right? Every day there's earthquakes somewhere in the world. We only hear about the ones that happen near people. Yeah.
I imagine that would be quite the bias then. But so actually great. So something that we think about a lot, I think about a lot, is Australia is the continent. My perception of Australia, the continent, is that it's this landmass at the centre of a plate, not necessarily near its edges. So when we think about dynamism and diversity of process and landscape, we often look at the edges of plates and the tectonic activity that's occurring at the edges of plates. And I don't think of that when I think of Australia. equally, I don't think of lots of densely populated landscapes. Like, I don't think of lots of densely populated regions in Australia to even pick up on dynamism like an earthquake. So can you help me think about that?
Yeah, no, it's a great question. So absolutely, the largest magnitude earthquakes and the frequency at which earthquakes occur is highest along plate boundaries, the edges of the plates. That being said, within the interior of a plate, we can still get some earthquakes, and Australia does get, shock to people, Australia does get earthquakes.
And big, like, are we talking like little earthquakes or?
Yeah, so we've had, so for example, anywhere in Australia, magnitude 3 and above earthquake, about 100 per year are recorded.
Decent.
Sort of order of magnitude, which is, decent. The largest that's ever been recorded, magnitude 6.6.
That's huge.
Yeah, which is a sizable earthquake. That was in Tennant Creek.
Very densely populated.
A dusty little town in Northern Territory. Amazing.
So there's certain, it's not in Australia, it's not completely uniform where the earthquakes occur. It's not as localized as a plate boundary, but it tends to be in certain zones, tend to be in Australia, some are more relatively active than others. So South Australia and Adelaide is one of those places in the context of Australia where it tends to get more earthquakes. So some of your listeners may have felt earthquakes.
Absolutely.
I don't know if you guys have ever felt an earthquake here.
Yeah. I felt a little one from we call them the Adelaide Hills, the sort of very tiny mountain range out. That's such a joke.
No, just keep going. I shouldn't have said that. It is a tiny mountain range.
Absolutely. And but yeah, my mind just goes, that's weird. I don't understand. Well, at the time I didn't understand why there would be earthquakes here, but I would like to go back to your point about they're not uniformly distributed around the country. That feels like something I want to explore with you.
Yes, yeah. So they tend to be in areas where there's lots of old faults. So,
and a fault on the biggest scale, what's a fault?
What's the biggest?
Where the earth has broken.
Where there is a very large fracture.
A weakness.
A weakness. Yeah, that's good, Anthony.
Nice.
I got a tick today.
You have a rock. You've broken the rock in a linear, planar sense.
Yeah,
let's say.
And you get earthquakes along those.
Now, a plate boundary is somewhere where you have a let's say a giant fault or fault, mega fault, yeah, where you have relative movement between the two plates on either side. Australia, we don't have that, right? Australian continent is a stable continent. It's all one entity, but it hasn't always been in the same configuration it is. So Australia was pieced together from different blocks, different building blocks to form the continent. And those have left along those boundaries where they join together. Those have left significant tectonic boundaries or significant faults, or where there's been past plate boundaries, past deformation, created lots of faults and breakages. So, now, that's the sort of, imagine you had 2 bricks and then you had some like,
what is it called?
Like Play-Doh or like silly putty that's in between them. So that's kind of your fault, your weakness.
Yeah.
So 2 blocks are moving together today. But then you imagine where Australia is. We're surrounded by plate boundaries. So we've got New Zealand to the east. We've got Indonesia to the north.
There's a huge amount of activity surrounding us,
and then
actually.
To the south, we've got the Australia-Antarctica plate boundaries. So we're actually encircled by plate boundaries. So those plate boundaries, what's happening there, those movements are then creating from the distant forces. So we're kind of pushing and squeezing and pulling on the Australian continent. So if you go back and think of those 2 blocks with kind of silly putty in between, if you're squeezing and pushing that, then those weaknesses will start to move to adjust to those distant forces. So that's what's happening, which is really interesting. It means they're not as frequent as the plate boundary earthquakes, but we do get motion on them. But it also means that it's much harder to know where there might be an earthquake. Right? We know where the plate boundaries are. We have some knowledge of where there are faults, but as you said before, a lot of Australia is covered by sediment, kind of massed. So a lot of these old faults, we don't even know where they are. So often in Australia, when earthquakes happen, they can be quite a surprise. And the
Even to the seismologist, the fault is a surprise. Isn't that interesting?
Yeah.
It makes me think of, say, for example, the earthquake that happened in Christchurch a while back. I can't remember how many years it was, but that seemed
devastating earthquake.
A devastating earthquake. The very bad one that happened in the last 10 years or so, or maybe longer.
In New Zealand.
In New Zealand, New Zealand.
Yeah.
And I seem to remember that example, that fault wasn't really known of either, right?
Yeah.
So it's a similar. I'm not saying it's the same scale of problem because they're right on a plate boundary, but internal to the continent, you're saying there are potentially lots of different faults which are kind of perhaps relict or like relict of a previous tectonic activity,
that's a good word for it,
which may be active. So is there like you must have maps of hazard, right?
Yeah.
And how reliable and how do you, what do you think about in terms of that?
Yeah. So that's a lot of work that happens at Geoscience Australia. They produce these national models of seismic hazard in Australia. And part of that is based on where we know there are faults, where they can be mapped at the surface. And the other part of it is based on where there has been earthquakes, then you're more likely to get another earthquake. But there's still remains that anywhere in Australia has the possibility. And I think what's interesting is if you look at our different capital cities, so Melbourne, Sydney, Canberra, Perth, Adelaide, they're all in these places where we do get earthquakes.
Interesting.
So it's not, I think, the important work that Geoscience Australia do of building these models so that can be incorporated into building codes for, understanding the potential. But there's also important in the older capital cities where you have these older buildings, particularly brick buildings that haven't necessarily been, at the time that they were built within the knowledge of these earthquakes.
Literally. So my family, my mother and sister would say that we live in a haunted house, and because there are cracks and suspicious movement that happens in the house, and there's cracks that appear, and it could be like the layer of soil or whatever that it's built on. But I logged on and I went to the geological spatial maps, and I see that we're actually sitting on a big fault line, and so I go the geological magic. It's not haunted. It's geology. Anyway,
you're not right on top of the fault, are you?
Honestly, if the two streets are like this, it goes
pretty close.
It's pretty close. I just want to pulse check my understanding here because I think this is a bit abstract what I'm thinking, but I think it's quite lovely to think about it like this. So your comment about the Christchurch earthquake, please correct us if this isn't completely right, but my understanding is that you're right. It wasn't necessarily along a crack that they had pinned as the crack to go, but it was related to the big cracks that they thought could go. So in that sense, the earthquake was happening in a series of edges, in a place where things are changing.
Yeah.
And if you look at the seismicity of the Australian continent, you scratch your head and you go, well, there's earthquakes here, but on the surface, I can't see much changing. So what is changing in the subsurface to allow there to be a break, an expression of that energy release here? And the answer to that question comes with a assessment of deep time, of deep tectonics, because the intact Australian continent as it looks today is not necessarily intact a few kilometres, hundreds of kilometres below the surface.
Yeah. I guess you say some parts of it are stronger and some parts of it are weaker. Yeah.
Yeah, cool. Yeah. So, okay, what are the biggest building blocks of the continent then? So, like, what if you had to draw the big cracks, roughly where are they? Are we in a block?
Yes. So there's different components of this. At the broadest sense, we're sitting on what's called the South Australian Craton. So these oldest regions are called cratons. We're sitting today on the South Australian Craton. Western Australia forms its own craton. And we also have the Northern Australian Craton. So the biggest boundaries, those separate the sort of different ages of different regions with boundaries in between them. But even within those, those are also made up of separate blocks and fragments that have been fused together. And it's really all those little, probably a lot of those boundaries or internal boundaries and faults and things that we see the earthquakes.
Just like never-ending cracks.
It's the Russian dolls kind of analogy of cratons within cratons.
Correct.
Yeah.
So my understanding is you do pretty cool work in Western Australia at the moment.
What's going on?
Yeah. So, I mean, I think this is a really exciting time for Australian seismology. So I'm involved on a project that's being led by the Geological Survey of Western Australia. And they're doing a project called the WA Array. And what they're doing is they're covering, in the next decade, they're going to cover the entire state of Western Australia with broadband seismometers at 40 kilometres spacing. Huge. So to put this in context, Western Australia is a third of the continent. So this is huge scale. And by the time they finish this, it will be over 1,500 sites or seismometers. And it will become one of the largest, or comparable, one of the largest continental scale seismic arrays in the world. So I think this is fantastic.
It's huge.
I think, we've certainly done, there's been a lot of, over the decades, work from ANU, the group that I'm in, other different institutes and surveys have done their own work of trying to piece together different parts, different surveys. But to do this kind of coordinated, longer term, systematic survey, I think is just going to be amazing. And I think by the end will transform our understanding of this older, really thick part of the continent, and understanding it really. Imagine it's like putting on a pair of glasses. You're suddenly going to see inside the earth in the resolution in a put everything into focus in a whole new way. And already, they've started in the southwest corner of Western Australia and kind of moving outwards. Already in this southwest corner, kind of around Perth, starting to image more variations of this kind of topography on the base of the continent, and really some interesting initial observations there, how that connects to then kind of mineral deposits at the surface. So that's been one of the driving questions of this, is the connections between what this deeper part of the continent looks like, how that influences things like fluids and mineral systems that come up and then we find closer to the surface.
I just want to clarify a little bit, just one step back, and that was about the comment about Christchurch. I was just, as you were talking about Western Australia, I was thinking I shouldn't clarify that. It's all about scale, I think. So there's big cracks. The people in Christchurch might say, well, we're a long way away from the main fault, and they are in a sense. But what we're talking about here is hundreds to thousands of kilometres away from the main fault zone, whereas they're a little bit closer. I just wanted to clarify that.
No, well, that kind of links in. I was going to ask a selfish question on, actually, would you like to continue?
I was going to say how amazing it is to have this opportunity that Australian science is supporting this, and the government's organisations in particular. This is some of the most heavily mineralised and geologically interesting crust in the entire world. It's some of the oldest crust.
Some of the oldest crust in the world.
Some of the oldest crust in the world. And so the sort of processes that are preserved in these old parts of Western Australia are really seeing right back into the Earth's early ages. So, looking at that with with those clear glasses that you'll get from all this data, it's going to be absolutely incredible.
Yeah.
So exciting to work on.
Yeah. You make such a good point. Just rapid fire to help me frame this next kind of question. Rapid fire. What's the oldest bit of Australia sitting in WA? Is it what? A few billion years? How, 3? 2, 3?
3 point something.
It's 3.8 or something like that.
You know what gets
it? What are the Jack Hill zircons?
The zircons themselves are like 4.1 or 2 something. So they're little minerals, but the actual rock itself I think is about 3.8 or 3.9, something like that.
Right, and this is what gets me, because I feel like the physicists and the astrophysicists and the cosmologists have it figured out with sort of the grandeur of like the time and how old the universe is, and the telescopes and like the arrays that look into the universe, and we get to talk about
exactly.
Correct. It's sort of, we go, okay, that's cool.
Okay, you can your quasars and your
correct. You can stargaze all you want,
but
the geological time and huge scales that this kind of project is peering into is literally comparable to cosmic time scales. So it's huge.
No, we often talk about, I try to frame it in that way. It's a telescope pointed inside the Earth instead of looking outwards towards space. Right?
Yeah.
It's comparable in kind of scale of the projects, and what you're trying to do is an inward pointing telescope is sometimes how it's referred.
So what's that like for you? Like for you as Carolyn to be involved in this, did you know that this sort of, did you know as an 8-year-old that seismicity was what you were going to be interested in? To grow into this kind of science and to now be involved in such a cool project with this huge amount of collaboration, what's that been like for you?
Yeah. No, I had no concept of seismology, or I wanted to be a seismologist until I was at university.
Yeah.
I can talk more about that. But I mean, I first got into it, I did go and study geophysics as undergrad. And I really got into that because I was just really fascinated by the Earth. So sort of looking around where I live, understanding the different, I was really fascinated by the different like physical processes and what had shaped the world that we kind of see around us. So I really was really fascinated by like Earth processes. And then, but I was also good at maths and physics, and I was kind of reading. I was reading like, you know, like university prospectuses, like different like subjects, and I came across geophysics, and I was like, aha, this like combines my, you know, interests. So yeah, let's do this.
Amazing.
Yeah, so that worked out.
And obviously,
certainly did.
Yeah. But also you grew up in Ireland, so not even in Northern Ireland, not even in Australia. Yeah. That's cool.
No. So no concept of, you know, there's no relevance there of seismology to daily life.
Oh, is that harsh or is that actually true? Is there,
I know there's more people, a couple more people now, but I mean, I could definitely count on one hand the number of Northern Irish seismologists.
Carolyn, and she's in the room with us.
You've got him on speed dial on the.
A couple more people I know, but not even many Irish ones, but a few more. Yeah, so it's definitely quite unique in that aspect. But what changed for me was when I was studying, I did a year abroad, and I did a year abroad at Berkeley in California.
I see.
So
very seismically active.
Very seismic.
Place.
So I did took seismology classes there, right on San Andreas Fault, and there's a sub branch of the San Andreas Fault called the Hayward Fault. Where I was living when I was at Berkeley is a place called International House, and it was right next door to the stadium. And the stadium in Berkeley is really famous because the Hayward Fault runs right through the middle of the stadium. And they actually measured, it's actually like cutting it in half very, very slowly. So they actually have to kind of like, at the ends of it, they kind of have like steel plating to kind of like put a plaster over it and stick it back together.
They're repainting the lines on the stadium floor.
Yeah, because it's just very, very slowly creeping. So I was living right next to this, basically like looking at it.
Watching it break.
So I learned all about it, and I was working there, and I had to do a project whilst I was there. And I ended up doing a project with a seismologist and in the seismology laboratory there. And that's where I first started doing the type of work that I still continue today. And I just loved it.
Amazing.
I just was fascinated by everything seismology, everything plate tectonics. And I loved the project that I was doing where I was studying, I was actually working on a subduction zone, the Cascadia subduction zone along the west coast of North America, and looking at mantle flow in that subduction zone. And I just loved it. And that's kind of, then I continued from then. You know, after that, went back and was like, no, I want to do a PhD in this. And it kind of set me on the path of where I am today. Yeah.
Isn't that so cool to hear about your roots actually looking at this fault break the stadium in half to end up in Australia where you actually have to peer really, really deep beneath the surface to understand these big cracks, these big weaknesses, why Australia shakes. Thank you for coming in. Thanks for being so generous with your time and your science. It's just so cool to talk to you, Carolyn. So thank you.
Thank you.
Thank you so much for having me.
Cheers.